Hi there, this is Matt Heffernan. Welcome back to my channel. This is the 11th episode in a series that seeks to demystify programming and assembly language for the 6502 family of 8-bit processors. We're using the Commander X16 as a target, as it has a 65C02 and is a particularly excellent platform for this learning process. If you haven't seen the previous episodes and need to start at the very beginning, please go back to my channel. Don't forget to subscribe and click the bell for notifications while you're there so that you know when the next episodes come out, and start this playlist from the beginning. So far in this series, we have learned the fundamentals of assembly programming by going through the entire 65C02 instruction set and examining how each instruction works, and then how to do basic things with the kernel and the Vera display controller, including interrupts. One of the earlier episodes was an introduction to basic arithmetic and logic using the 65C02, where we saw that all math had to be done with just 8-bit addition, subtraction, and bit shifting. There are no instructions for multiplication or division, nor are there any instructions that can affect more than a single byte in memory at a time. In this episode, we are going to show how this very simple architecture is capable of doing all the math that is handled by more comprehensive instruction sets, thanks to being just complete enough to be able to implement algorithms for any mathematical operation. Of course, that doesn't mean it is fast or advisable to implement comprehensive algorithms. Today, we will learn how to tailor programs to our specific needs and make the 65C02 do just enough to do the required calculation with the required precision. Just like our grandparents during World War II, we can do larger scale math with an 8-bit CPU by simply keeping calm and carrying on. If your grandparents weren't alive during World War II, you are definitely outside my channel's usual demographic, but you've probably seen the old poster and can still take the message to heart. The carry bit is the main linkage between the different bytes in a value when doing any math operation. It lets us do math at widths of any multiple of 8-bit, as allowed by available RAM. With the X16, we have more than enough RAM to do 256-bit math for a pretty large data set, but chances are that's not what you are trying to do. A humble Raspberry Pi will absolutely smoke the X16 when it comes to complex math. So the reality is you probably just need to go up to 32-bit values for any application. And even then, needing to go beyond 16 bits is pretty rare. Regardless of width, we need to manage the carry bit for performing arithmetic across these values, initializing it to the correct state, and preserving its state as you chain your operations from byte to byte. As we've seen before, for addition, we need to start with the carry bit clear, so the usual process is to do a CLC before your first ADC, or add with carry. ADC will add a 1 to its sum if C is set, and will then set C if its sum is greater than 255. This will do a carry to the next addition, which is exactly what we want to do when doing an ADC for the next higher byte. So doing a 16-bit addition follows the process you see here, with doing a CLC at the beginning, then doing an ADC for each pair of bytes, allowing the carry to propagate upward. This example assumes both operands are little endian, and will produce a little endian result. You could just as easily deal with big endian values by reversing the order of load, add, store operations, just as long as you are starting with a clear carry bit and the least significant byte. We also saw before how subtraction uses the carry bit for borrowing, and is inverted from how it's used for addition. You need to start with C set, which you can do with an SEC before your first SBC, or subtract with carry. SBC will subtract 1 from its difference if C is clear, indicating a borrow is needed for the subtraction of the previous pair of bytes. Just like with ADC, we can chain SBC instructions together by maintaining the carry bit as we continue through higher bytes. Right here is an example of a 16-bit subtraction using little endian values. We start with C set, then use the state of C output by the first SBC as the input for the second SBC, performing a borrow if necessary. Every time you shift the bits of a value one space to the right, you are effectively doing a division by 2, as long as you are filling the most significant bit with 0. So dividing a multi-byte value by 2 requires you to do an LSR, or logical shift right, on the most significant byte, and then an ROR, or rotate right on each successive lower byte. This will shift a 0 into the top and then carry the lowest bit of each byte into the highest bit of each lower byte until we get to the least significant byte, where the final state of C will indicate what the lowest bit was that ended up shifted out. Here we see how we can take one little endian 16-bit value and have it divided by 4 and stored in another 16-bit location. We take the high byte of the original value and do an LSR and store that to the high byte of the target value. Then we take the low byte of the original, do an ROR, and store that in the low byte of the target. At this point, the target value has the original value divided by 2. Now we no longer need to refer back to the original value, and we can shift the target value one more time right in place, again with an LSR for the high byte, followed by an ROR on the low byte. In this case, we can see that whatever bit got shifted out with the first ROR is simply lost. It will not factor into the subsequent LSR, which will always shift in a 0 at the top. We could keep track of the bits that are shifted out with each ROR to have a fractional value for the division, but for integer math we just let them get lost. When you shift to the left, you are effectively multiplying by 2 for each bit, as long as you are filling in the bottom with zeros. This can be accomplished with an arithmetic shift left, or ASL, on the lowest byte, and then using ROL, or rotate left, on each higher byte, which will shift in the bits that were shifted out of the lower bytes. If your top bit is already set, then the target of your shift will need to be wider to still have a proper multiplication. Generally, the product of the multiplication needs to be as wide as the widths of both factors put together. So two 8-bit values can multiply into a 16-bit value. In this example, we are multiplying a 16-bit value by 4, which means that the result could end up being 24 bits. This could be captured by adding additional ROLs to a third byte for each shift. But if you know your code won't be multiplying a value greater than 16,383 or hex 3 FFF, then you know you can safely keep it to 16 bits. When you are dealing with an 8-bit machine with limited memory, you don't have the time and space to do anything unnecessary. All the math we have seen so far has been with integers, and we've been ignoring any fractional values in between whole numbers. On a modern computer, we would address this with floating point math, using built-in support for single and double precision floating point in the instruction set, and then with high-level languages that have syntaxes similar to standard mathematical notation. For most 8-bit machines, floating point support is provided by BASIC, as it is with the X16. Commodore BASIC and its derivatives like Commander X16 BASIC actually handles all numbers as floating point, even when integers are specified in the code. Of course, this is one of the many things that makes BASIC slow, and assembly the preferred language for creating even more complex applications. That means you have to do everything as 8-bit integer math and make that work for your needs. You can still do floating point by hacking away into the library found in BASIC ROM, or rolling your own implementation. But for most cases, using fixed point is going to be more desirable. Fixed point means that you are still doing integer math, but redefining your numbers to have a fixed number of bits at the bottom dedicated to a fraction. For instance, you could do a fixed point implementation with precision of 1/4 instead of 1. So the lower 2 bits of your value are the fraction, meaning 1 would have a value of 1/4, 2 would be 1/2, and 4 would be 1. This, of course, limits your upper range by the number of bits you are using for your fraction. So an 8-bit fixed point value would max out at a value of 64 with 1/4 precision. But then you can use these values just as if they were integers, adding and subtracting them without any regard for their interpretation. Things get a bit different from multiplication or division, but if your operand is an actual integer value, then it will work the same in that case as well. So in these cases, fixed point is just as fast as integer math, and much faster than floating point. But floating point still has value for some applications, and does work for a much wider range of values. The precision is based on significant digits, as the value is split between a mantissa for precision and an exponent for range. So you can work with very small values and very large values and not have to change your arithmetic routines or storage. This is why BASIC uses it as a lowest common denominator for all use cases, at the expense of memory and speed. For each use case, you will likely have to roll your own fixed point implementation and use a format of your own invention, whereas your one floating point library can be reused for all cases and comply with common standards like IEEE 754. The bottom line is that anytime you need to use fractional values in your application, you need to take the time to analyze your needs and decide on a representation that is going to work the best. Getting back to integer math, we saw how we can multiply by powers of 2 with simple bit shifting to the left. But what about multiplying by an arbitrary integer value? You don't want to do a brute force addition loop, as that could take an enormous amount of time as you deal with wider values. All you have to do is factorize your multiplication into a sum of powers of 2. After all, that's all binary data is, expressing values as the powers of 2 that compose it. So we can still just use shifting to come up with each of these factor products, but then add them all together to get the whole product. For example, we can calculate 10 times 25 by multiplying 10 by each power of 2 component of 25. We can split up 25 into 16 plus 8 plus 1. So 10 times 25 will be the same as 10 times 16 plus 10 times 8 plus 10 times 1. This gives us 160 plus 80 plus 10, or 250, which is just what we would expect. This process can be done entirely with shifting and addition, which becomes more apparent when you look at the problem in binary, as you see here at the bottom. 10 is represented as 00001010, and 25 as 000110001, where you can see the 16, 8, and 1 bits all set. So we break that up into those factors with just 1 bit set, and you can see how each multiplication is a shift to the left by the number of zeros you see after the 1. So we know that we need to shift 10 4 bits to the left to multiply by 16, 3 bits for 8, and no shift for 1. Then we just add all 3 products together, and that's easy in this case, as there aren't any common bit set between them, and we get the result 11111010, which is hex FA, or decimal, you guessed it, 250. But how do we actually code this? There are several different approaches, but we're going to look at one right now that does all the arithmetic operations we just saw. We want to have a subroutine that will multiply the values in the X and Y registers and store the product in a 16-bit word in RAM that we have creatively labeled product. I won't go into a line-by-line explanation right now, but you can see that it takes quite a bit of code. These slides are all in the GitHub repo linked in the description, so you can take a closer look there. But in short, we first put the X value in the product and then check Y to see if it's 0. This algorithm won't work unless at least 1 bit is set, so instead we just branch to the end to simply write 0 to the product and be done with it. Otherwise, we store Y in a temporary variable, which we shift to the left until we find its highest set bit. This tells us how many times we're going to need to shift product before we are done. Then we shift it back to see what other bits are set. As we shift the product, we check to see if the bit for the current power of 2 is set in temp, and if it is, we add the current value of product to another variable called offset. We keep on shifting product and adding it to offset when applicable until we were done shifting. Then we add the offset to the product that has been multiplied by the highest power of 2 that was found. This will give us the full 16-bit product of any 2 unsigned 8-bit values, but it takes up a fair amount of code and is not exactly super fast. So chances are you don't want to do exactly this in your own program, but maybe some sort of modified and optimized form that works for your specific use case. In our example program later, we'll see a full 16-bit version of this algorithm and go over it in greater detail. When it comes to division, we can't just deconstruct the right-shifting process that lets you divide by powers of 2. Math doesn't work that way. If you want to divide 30 by 5, for example, you can't just divide it by 4 and 1 and combine that like you can for multiplication. That kind of transitivity doesn't exist for division. Instead, you have to work backwards, building up the powers of 2 that will make up the quotient. We can determine this by shifting the dividend into the remainder, and then seeing if we can subtract the divisor from it for each power. If it doesn't make a lot of sense on its face, that's okay, but effectively we can say that for this example, 4 and 2 will let you do this, making the quotient 6 with a 0 remainder. The best way to show how it works is to just lay out the algorithm, so let's do that. For division, we know that the quotient won't be any bigger than the dividend, so if we are starting with a 16-bit value, our result will also fit in 16 bits. In fact, both results will, as this algorithm produces both the quotient and the remainder of the division. To start, we need to set both result values to 0. Then we start a bitwise loop through the dividend. For each iteration, we double the quotient and shift the dividend to the left, and shift its top bit into the bottom of the remainder value. If the new remainder value is greater than or equal to the divisor, we store the difference into the remainder and increment the quotient. Once we go through each bit of the dividend, we will have the final values for the quotient and remainder. Trust me, it works. Let's take a look at how we can code that. To implement this algorithm for 8-bit values, we can do a division with a pretty small amount of code, especially compared to multiplication. Here we define a subroutine that will divide x by y and place the quotient in a and the remainder in a RAM variable. We also define RAM variables for the quotient and divisor, as we can't just keep them in the registers the whole time. We start the subroutine by storing the dividend in x in quotient, where it can be shifted out and eventually replaced by the actual quotient. Then we store the divisor in y into its RAM variable, initialize the remainder to 0, and load x with 8 for our loop index. We start the loop by shifting the quotient to the left and rotating its top bit into the remainder. Then we subtract the divisor from the remainder, and if the carry bit is still set, store the difference in remainder and increment the quotient. If the divisor was greater than the remainder, then the carry bit would have been cleared by the subtraction and we would just branch straight to @shift_next. There we end each iteration by decrementing x and branching back to do the next iteration until x is 0. Once x is decremented to 0, then we know that the whole dividend has been shifted out of quotient and replaced by the actual quotient that was built by the increments that happened. We finish by loading the quotient into a and returning. If there was a remainder, it will still be in remainder at the end. Now that we have seen how to do all kinds of integer arithmetic, we need to be able to present results to the user. Unlike you and me, most users aren't keen on reading hex numbers in their interface. For this, you'll need to convert our binary numbers to decimal strings. But that's not a simple thing to do. Luckily, the 65C02 has a decimal mode, where it has native support for binary coded decimal, or BCD values. Unlike binary numbers, BCD numbers are not mathematically consistent. Instead, they are built to look like decimal numbers when displayed in hex. For example, the number 1234, when expressed as a binary, has a hex value of 04D2. A BCD representation will actually have the hex value 1234, which means it becomes trivial to convert it to a decimal string by making each nibble a character. To use BCD values, you can put the 65C02 into decimal mode with the SED, or set decimal instruction. This sets the D bit in the processor status and affects the behavior of the ADC and SBC instructions. The rest of the instruction set is unaffected and will continue to treat values as binary. Once you are done doing BCD math, you can exit decimal mode with a CLD, or clear decimal instruction, which will clear the D bit. Then, with a BCD value, you can simply print it as ASCII or PETSCII by pulling out each nibble from the most significant on down and OR it with hex 30 to get the corresponding number characters. You can also use decimal mode to convert binary values into BCD using a simple and fast algorithm. So we're going to write a subroutine that will print the value in the accumulator as a decimal string to the screen. To do this, of course, we need our old friend carout to do the printing, and then a couple variables to do our work. Bin to hold the binary value we are converting, and BCD to hold the resulting 16-bit BCD value that could contain 4 decimal digits. We label our subroutine print A and start by storing the value in A to bin and initializing BCD to 0. Then we load 8 into X for a loop index and go into decimal mode for our loop. For each iteration, we shift bin to the left and use the carry bit holding the previous top bit of bin to add to BCD to itself, incrementing the sum for each bit that was set in the original binary value. This means we are doubling the BCD value for each iteration, and each power of 2 in the original binary value is getting added to the BCD value at what will eventually be its full value thanks to the doubling. Once X gets down to 0, we fall out of the loop and exit decimal mode. Then we call another subroutine called print byte with the high byte of BCD already in the accumulator. This will print the value in A as hex, assuming that it will never have to print any letter characters. Then we load the low byte of BCD into A and call print byte again. This should print out a complete 4-digit decimal number with at least one leading 0 because we know that 255 will be our highest possible number. For print byte, we push the value in A onto the stack to save it before shifting it to the right to move the upper nibble to the lower nibble. Now with a clear upper nibble, we OR in hex 30 to make it into a Petsky number character and call carout to print it. Then we pull the original value back into A and clear out the upper nibble with an and replace it with hex 30 again to print out the next number character. With both digits printed, we return, and that's it. Pretty much every time you see a computer output a decimal value, it's going through a process very much like this. Now we're ready to use what we learned here to make a simple example program that will take two 16-bit values and multiply them and print out the resulting 32-bit product as a decimal number. This will use hard-coded values for the factors, but this lesson's material also includes an extra example program that is a full 4-function calculator, letting you add, subtract, multiply, and divide 16-bit positive integers based on user input. For now, let's go to the text editor and take a look at the simpler multiplication program. Okay, we have the usual segment preamble and jump start, then get into our constants. We only need a few to deal with printing our results, with carout as the only kernel function, and the Petsky codes for return and the 0 character. Then we have some global variables that will be used for doing multiplication and conversion to BCD. We hard-code our two 16-bit operands, then define two double words for the result of the multiplication and the offset that will be used during the algorithm. Double words are 32 bits, so this will give us enough room to replace those operands with any 16-bit values and be able to calculate their full product. Then we reserve 5 bytes for the BCD conversion of the result, as a 32-bit binary number can have as many as 10 decimal digits. Finally, a couple of temporary variables for different purposes that we will see soon. At start, we can see our very short main routine. We simply call the multiply subroutine followed by print result, then return back to basic. We start multiply by copying the second operand into result and zeroing out the upper 2 bytes just in case this program had been run before. Then we completely zero out offset and copy the first operand into temp word. After copying the high byte, we branch to @op1 byte if it was 0. This means that op1 is only a byte, and we need to look in the lower byte to find the highest set bit. Otherwise, we know at least one bit is set in the high byte of op1, so we go looking for the highest one there. To determine the exponent of 2, we need to ultimately shift to factor into the result. So we load 16 into y and start our high byte shifting loop. Each iteration we decrement y and shift the high byte to the left. If the C bit is still clear, then we haven't found the highest set bit yet, so we branch back to the top of the loop to keep shifting. Once C is set, we are done shifting to the left, so we store the value of y to another temp variable so that we can subtract it from 16. This will tell us how many bits to shift it back to the right, which we will transfer to x for the next loop index. This loop will shift that high byte back to the right and decrement x until it gets back down to 0. At that point, we know the high byte has been shifted back to where it was, only now with what used to be the highest set bit cleared. So we fall out of the loop and branch unconditionally to @shift. If the high byte was already clear, we would have skipped these last two loops and branched right to @op1 byte. We first load the low byte and check to see if it's 0. If it is, then we know the whole operand is 0, and so our result will be as well. We go ahead and zero that out and jump ahead to @return. If it was non-zero, we're going to need to do another loop to find the highest set bit. This time, we load 8 into y as that will be the maximum exponent and then enter the loop. This loop is just like the last one we did to find the exponent, but this time we are shifting the low byte until we find the highest set bit. Once we get that bit shifted out, C will be set and we fall out of the loop, subtract the value in y from 8 and put that into x. Now we shift it back using x as a loop index, just as before, until the low byte is now back to where it was, and y contains the exponent and temp word contains the remainder to multiply by after the exponent is applied. Once we get to @shift, we are starting a new loop that gets called after either the high or low byte of temp word has had its highest set bit cleared and its position is in y, which we use as a loop index. We start each iteration by checking to see if y is 0 yet. This could happen on the very first iteration if op1 was set to 1, meaning the value of op2 is already in result and offset is 0, so no actual multiplication needs to happen. Otherwise, we go on to decrement y, then shift temp word to the right to see if the bottom bit is set. If it isn't, we skip ahead to @shift result. Otherwise, the value currently in result needs to be added to offset. As this will be a 32-bit addition, it will be less code to do it in a loop. To set up this loop, we initialize x to 0 for our index, and clear C like we would for any addition. Then we push the status to the stack, as our loop has a comparison in it that can change the state of the carry bit, and we want to make sure that only the ADC instructions are controlling it. Once into the loop, we pull the status back down and do the addition for the current index, storing the result back into offset. We push the status again for the next iteration, then increment x. Comparing to 4 could change the state of C, so good thing it's on the stack. If x is not 4 yet, we branch back to the top of the loop to continue adding the higher bytes together until the full 32-bit addition is complete. Once we fall out of the loop, we still have the status on the stack, so we pull that off one more time to clean up. We don't really need that status anymore, so it could have been pulled into A, but we might as well be consistent. Then we get to @shift result, which we may have skipped right to if the lowest bit in temp word wasn't set before we shifted it last time. This will shift result to the left across all 4 bytes, and then branch back to the top of the loop as we know that y is not 0 yet, and we'll have to do this shift at least one more time. Once we have y down to 0, we fall out of the loop to @remainder, where we need to finally add that remainder in offset to the result. So we do another 32-bit addition loop, but this time we are storing the sum into result. Once we fall out of the loop, we have another status again on the stack that needs to be pulled off, and our multiplication is complete, so we can return. With the result variable now set in binary, we can use the print result subroutine to print its decimal value. But first we need to convert it into BCD, so we're going to do an expansion of the algorithm we saw earlier. We start by initializing BCD to 0, then entering decimal mode and loading 32 in x for a loop index, as we need to loop through all 32 bits of the binary result. We start each iteration of the main loop by shifting result to the left, putting the top bit into C. We need to add this into the 5-byte BCD value, so we need to do a subloop for the addition. We're going to use y for this index, then push the status to the stack so that we don't lose the value of C. We add each byte of BCD to itself with the carry that came from the earlier shift, which will effectively double the BCD value for each iteration of the main loop, and possibly adding 1 to it. Just like the wider additions we saw before, we pull the status off the stack, do the addition for the byte at this index, then push the status back to the stack, which may have C set again after the decimal addition. Once y gets to 5, we know that we have finished doubling the whole BCD value, and we fall out of this subloop and pull that last status back off the stack to clean it up. Then we decrement x and branch back to the top of the main loop if we still have more bits to shift, and add into the BCD value. Once x gets down to 0, we fall out of the main loop and exit decimal mode. Now it's time to print the decimal value, but we want this program to be a bit more polished than the case study we saw earlier. This means omitting the leading zeros in the values, so we need to find what the first non-zero digit is. Of course, even our BCD value is little endian, so we start our search from the far end by initializing y with 4 for our loop index. In each iteration, we load up the BCD byte, and if it's non-zero, we branch out of the loop to check upper. Otherwise, we decrement y and keep going back to the top of the loop to check the next byte, until we either find a non-zero byte or y itself gets down to 0. If the latter happens, we fall out of the loop and load the last byte and continue with that, as we still want to print out a 0 if that is the actual value. At check upper, we do a bit on the upper nibble, and if that's clear, then we branch ahead to @print lower. But if it wasn't clear, we continue on to @print upper, where we push the byte to the stack, then shift the upper nibble to the lower nibble, and OR in the Petsky code for 0. This gets us our desired number character, and we go ahead and print it with care out. Then we pull the byte back off the stack and fall to @print lower, which we would have branched to earlier if the upper nibble was clear. Here we just clear out the upper nibble with AND, then OR in the 0 character again to print this decimal digit. Once we have printed out the first 1 or 2 digits, we continue to print out the rest of the number. We decrement y, and if it goes negative, we branch straight to @return as we have no more digits left. Otherwise, we load the next lower byte and branch back to @print upper and print both of its digits, even if the first one is 0. Once we finally roll over y, we can fall out of the loop and branch to @return, where we print a return character to start a new line, then actually return from the subroutine. And that's it for this program. Of course, we have a build script, and this program will be built as multiply.prg. But you see, after that, we build calc.prg, which is the full 4-function calculator I mentioned earlier. We'll see that in action too, but first we need to go to the terminal and build our code and run it. Let's run build.sh, and then we'll check our directory listing. And there we can see multiply.prg and calc.prg, so we're ready to start the emulator. Alright, now let's maximize that so we can get a better look. Okay, let's load multiply.prg and run it. And there we go, 7,006,652. We can check this with BASIC by doing a print 1234 times 5678. And we can see that we got it right. Even more importantly, even though it's hard to tell with a single operation, our program was much faster. If we were to loop through hundreds of integer multiplications, it would take a fraction of the time that it would for BASIC to do it with floating point, as that's all it can do. Now let's go ahead and load calc.prg. And run it. Oh, now we have something like a user interface. Let's go ahead and do the same operation. We'll enter 1, 2, 3, 4 for the first operand, then hit enter. Now we'll put in 5, 6, 7, 8 for the second. Here we can type in which operator we want to apply. In this case, an asterisk for multiplication. And there we go again. Nice. let's keep this up with other operations. We can just run it again, and we'll do the same operands. 4, 5, 6, 7, 8. But this time with a plus for addition. And look at that, 6,912, which is correct too. If you don't believe me, we can ask BASIC. Print 1, 2, 3, 4 plus 5, 6, 7, 8. And yeah, still 6,912. So let's keep it up and run it again. Same operands, 1, 2, 3, 4, 5, 6, 7, 8. But this time we'll do a hyphen for subtraction. Hey, look, we have a negative value. We didn't account for that in the multiply example, but we have it in this one. Let's round it out and do a division. Run again, same operands, 1, 2, 3, 4, 5, 6, 7, 8. And now a slash for division. And yep, we get a 0, as the true answer is just a fraction, making the integer quotient 0. So let's do this one more time, but we're going to flip around our operands. 5, 6, 7, 8, 1, 2, 3, 4, and that forward slash again. And there we go, 4. Just for you, I'll do it in BASIC and see what we get. Print 5, 6, 7, 8, bye bye, 1, 2, 3, 4. Well, we got the integer quotient right, but the floating point implementation of BASIC gives us a bunch of digits past the decimal point. That may be more accurate, but a lot of the time we don't need that much accuracy, and the integer value will be good enough. If you want to see the code for the full calculator, you will find it right in the repo, but I won't be going through it in this video. If you want to see a line-by-line walkthrough of that, I made an exclusive video for patrons that you can see if you join up at the Patreon link in the description. But as far as this video goes, we're done. We could keep going with even more complicated math, but the building blocks you see here can get you most of the way as far as arithmetic goes. For more complicated things like trig functions, logarithms, and exponents, you may want to take advantage of the X16's banked RAM to make some big lookup tables for speed and accuracy. You can do any kind of math with the 6502, it just won't necessarily be fast or easy to implement. So our remaining lessons are going to move on to more X16 specific topics for taking advantage of the ROM software and all the different hardware devices. There's a lot more to come, and I hope you keep coming back and learning more. If you don't want to miss any episodes in the future, make sure you subscribe to my channel and click the bell to get notified when they come out. If this episode taught you anything, please click the like button, and if you have any questions, please put them in the comments, and that can influence how future episodes are made. If you can't wait for the videos to go public, become a patron and get access to new videos as soon as possible, just like the folks you see here did on my Patreon page, which you will find linked in the description, along with a GitHub repo containing all the materials for this tutorial series. Thanks for watching, and I hope to see you again soon. Bye-bye.